Okay, let's start the class. Oh, okay. Okay, today we're going to continue study power functions. So actually, this is a problem from 11.8. Is an interesting problem. Okay, here's a function. We define a function to be the series, okay, defined by this series. Okay, let me, I'm going to express as a sigma, okay? Start from 0 to the Cn, x to the nth power. Okay. So here's a coefficient, c to the 2k is going to be 1. And the c in the 2k plus 1, it's going to be 2. Right? So either 1 or 2. It's no. Okay. The question is, on what interval this series convergent? So the function is defined. Okay. Right? So if they're convergent to some number, then for the x, if the series convergent to some number, then you get value of f of x. So then the function is defined. All right. So it's very here we have to use either use a ratio test or use a rotor test, right? To find the radius. First, to find the radius of convergence first, right? Find the radius of convergence first, then you check the endpoints. So find the radius of convergence. Then you have two tests you can use. These are the ratio test or the rotor test. Okay, let's try use a ratio test. That's pretty common. Okay, this is my AN, right? So then I have a C n plus 1. Okay, this is a positive constant. And then absolute x. The question is, what is that limit? Okay. Now, in order to whether we can find a limit or not, we don't know yet. Okay, maybe there is no limit. Okay. So to find the limit, I have to start two cases. Either 2k when n equals 2k, right? The 2k plus 1 and c 2k. I know 2k plus 1 is 2, right? And k is just 1. So this is the value is 2. When n equals 2k plus 1, okay, even number, then the top one will be 2k plus 2. The bottom one is 2k plus 1. Okay, then that'd be 1 over 2. Okay, so this ratio is jump between 2 and 1 over 2. Either just takes this when n approaches infinity. Okay, when n is even, the value is 2. When n is odd, the value is 1/2. So the limit c n plus 1 over cn, this does not exist. All right, so it does not exist. Then we have a problem, right? I cannot find the limit, so we cannot use a ratio test again. Okay. Okay. The next one we can try is the rotor test. Okay, so the rotor test. This is a really good question. So the rotor test is going to be Cn, nth root, and absolute x. So the question is, does it have a limit? Does it have a limit? Okay. Does it have a limit? Okay, so right, this is the AN, right? So as we see there, AN is either 1 or 2, so it's between 2 and 1. Do you agree with that, right? Either 1 or 2, it's jump. That's fine. So the nth root is between to the 1 of n greater than 1 of n, right? Okay, now, oops, my Outlook is stuck. Maybe I have to restart. Okay, sorry. Just wait. I don't know, somewhere I touch it. Okay, so we're back. Okay. Okay. But when n approaches 0, this also approaches 1. So by squeeze lemma, right? So when n approaches infinity, 2 to the 1 of n approaches 1. So that forces the limit of the nth root of n is going to be 1. Great. So this time we do find the limit. No, I have to use a Cn instead of n. Yeah, n is the original. Sorry for that. Yeah, this is a Cn, Cn, and Cn. Okay. So the limit to the nth root of n, okay, n approaches infinity, is just equal to x, x. So clearly, the series, okay, this series is convergent if absolute x is less than 1, divergent if absolute x is greater than 1. Okay. So now, so how about when x equals 1? Right, when x equals 1, I think this Cn, right? This is clearly it's positive infinity because every term is 1 or 2. Of course, go to approach the infinity. It's obvious. When n equals -1, you needed to look at it carefully, okay? So this is going to be alternating series, right? I think we can do combine, okay? So this is divergent too, okay? This does not exist, okay? Divergent. Okay, why divergent? You have to take some more time to check. Actually, now I just realized that we can combine them into 1 because when absolute x is going to be 1, so the absolute Cn to the xn is going to be the absolute Cn. This is clearly it's not going to approach 0. Why it's not approach 0? It does not approach it because Cn is either 1 or 2, right? So this then implies this series is divergent by the nth term test. Okay, so my conclusion is the interval convergence is the open interval. Is going to be from -1 to +1. So over that interval, it defines a function. So f of x, right, is defined on this open interval, okay? So when you say I'm going to define function is a power series, then I can tell you, okay, this function is only defined for x between -1 and +1. Okay, that is about function. Now, how does this function look like? Can this function be expressed as an elementary function? I don't know. Okay. I don't think so. Okay. Can this function be expressed like some functions? But you can estimate this function, but this is a nice function. It's like a polynomial degree infinity, right? It's generalized polynomial. This is this function has very nice properties. Maybe can we find the derivative, right? Or can we evaluate the integral? You know, if we can express as a elementary function, right? So here we have an important theorem we're going to study today. Okay, this is a theorem. Okay. So we define this function f of x to be this, okay, and this function is defined on this interval where I is the radius of convergence. Now, maybe so the function is defined, you know, given arbitrary parameter power series, right? And there is a radius of convergence. So for x absolute x minus a is less than r, this function is defined. Now, this series may be convergent at the endpoint. I don't care. Okay, those are the, you know, that's sometimes convergent, sometimes divergent. Right, so this function is defined right now, right? Over the interval is a, this is a minus capital, is a plus capital. So it's defined on this interval. So now the function. So the function, the statement says that one, the function is differentiable, not only differentiable, this is going to be just the Cn times n x minus a to the n minus 1. Looks like it just differentiate each term. Okay. And not only that, it's differentiable for any x on this interval. So at the same time, the radius is, okay, here's the point. This power series on the right-hand side, the radius the radial convergence still R. Okay, so this holds for x in this interval, and okay, R is still the radius of convergence of this new, okay, of the series, okay, on the right hand side. Now, what does that mean? So you have a series, right? That you differentiate each term, you create a new series. But this new series, the radius divergence does not change, okay? So it's still defined, only defined on this interval, okay? Then I just want to say that this new series is actually the derivative of the function over there, okay? Clear, right? So now you give a series, right? And the series is convergent over that interval, open interval. Then that series I differentiate each term. Then I get a new series. The new series still have the same radius of convergence. And not only that, this new series is just a derivative of the function. Second statement, okay. This series, okay, I can use definite integral, okay. So it's going to be x f prime t dt. I can evaluate. This is a n plus 1 cn x minus a to the n plus 1. This one also holds for absolute x greater than r. Okay. And not only that, I is still the radius of convergence of the new series. So this, how do we get this new series? So we integrate each term, right? How do I get, right? No, this yeah, I put a note here. If you integrate t minus a to the nth power, right? And that is just equal to n plus 1 and x minus a to the n. Right. That's how do we get from? We get this, right? All right. Yeah, this is the true for n greater than equal to 0. Okay. Now, why is I just want to explain to you why the the radius convergence does not change. Yeah, we compare those two series, right? Yeah, let's look at this. Why they have the same convergence of the radius convergence? Maybe the interval convergence is a different endpoint, but why does this have the same radius? Okay, how do we find the radius convergence, right? We just look at the suppose, okay, it's not necessarily always the root test exists, but let's look at this, right? Okay, so this is going to be the nth root of Cn, and then multiply by absolute x. Okay, and if you assume, yeah, if we assume that this limit nth root exists, but not always. Okay, now we assume that, okay, this limit n approaches infinity exists. That's called C. Okay. Then the radius of convergence is determined by 1 over C. Then the radius convergence, because the limit is C, right? So this limit approaches C, and right, and the radius of convergence, this is less than 1 if and only if less than 1 over C, right? So this is the radius convergence. This is my radius convergence. This is how do we get it? But in that case, if you look at the series on the right-hand side, this is n, Cn, right? N minus 1. Okay. So I'm talking about this one on the right hand. I want to show you they have the same radius convergence. So I want to see what is that limit. Okay. Under this assumption, okay, under this assumption. Okay. Otherwise, the argument is pretty complicated. So this is going to be the nth root of n, then the nth root of Cn, then x minus a here is 1 over, okay. Okay. So now, you see that this approaches 1, this approaches C, this approaches x minus a. All right, so again, right, this less than 1 if and only if x minus a less than 1 over C. So that's why the radius of convergence is also 1 over C. They have the same radius convergence, right? So this is my radius convergence for the new series. I just explained to you in general, okay? This both series have the same radius convergence, okay? Now under the assumption, under this assumption, okay? Then you will question me, if this nth root does not exist, yes, then it takes a little bit more time to prove. I'm not going to show it to you here. Okay, so we just assume most of cases we assume this is a limit exists. Okay, you can construct example so that this limit doesn't exist. Okay, but you still can talk about radius convergence. Okay. All right, so let me. This is a interesting problem. Okay, so let's go back to the problem here. We define fx to be Cn, right? X to the power n. So C2k equals 1, C2k plus 1 equals, that is 1 or 2, yes. Yeah, it's equal to 2. Okay. So the radius of convergence is 1. In other words, f of x is defined on this interval, right? Now, in some cases, I just say if the series is convergent at one of the endpoints, so this function can be defined at the endpoints. For this particular series, it's convergent only on this open interval, so it's defined as a function. According to our theorem, it says that f prime x is going to be, f prime x is going to be this differentiable, not only differentiable, and I can have Cn and x to the n minus 1, okay? So this holds on this interval, okay? So the right-hand side, this series is convergent and to the derivative of the function, right? Now, what is the interval convergence? The radius convergence is still 1, okay? The radius of convergence is going to be 1, okay? Still the same, that's it. But the interval of convergence, okay, sometimes will be changed. But for this particular problem, I think it's still from -1 to the +1, okay? And here radius, the interval of convergence is going to be from -1 to +1. Okay, we just saw that, right? It does not, this series does not, is not convergent at the endpoint. So when you differentiate each term, you get a new series. The new series has the same property. Radius convergence I equals 1. Interval convergence still -1 to +1. Then and it's convergent to the derivative of the function. All right. So how about the integral? Okay. According to the theorem, the integral from 0 to x f of t dt. This also should be Cn n plus 1 and x to the n plus 1. This holds for x greater than 1. So that means this series on the right-hand side, the radius of convergence, I is still going to be 1. Okay, that's guaranteed by the theorem. Now let's just look at the series on the right-hand side. The series on the right-hand side, okay. Yeah, let's look at this is a good example. Let's just look at the series on the right-hand side. The left-hand side is just the integral, right, of the function. The series on the right-hand side may be convergent at the endpoint. Okay, so this series, when x equals 1, okay. Now this series is divergent when x equals 1 because Cn is between either 1 and 2. So I can say by the comparison test, it's always greater than or equal 1. So that's infinite, okay, divergent. right? Divergent. Okay. But then when x equals -1, okay, you will get now the question is whether this is a divergent or convergent. I think it's convergent, but the problem is Cn is not a decreasing, maybe. Okay, it's not a, see this part, you have to prove that it's decreasing. In order, yeah, the proof is not it's not easy. This is a challenging problem. Yeah, how to prove it's convergent because Cn is n or negative n, right? Clearly, the nth term approaches 0, so you have to go through the proof. Okay, you have to go through the proof. Okay. All right. Yeah, let me check, double check. So Cn, I think, yeah, 2k plus 1. Yeah, let's see, okay? So when n equals, yeah, this is going to be when n equals 1 over C, odd number, yeah, when n equals 0 to 1, okay? So when n equals 0 to 1, so minus 2 over 1, 2, right? Plus 1 over 3, and when n equals 2, when n equals 2, C2 is 1, C3 is 2, right? Something like that. Okay. So the question is whether this is going to be convergent. Okay. If we compare this pair, okay, I think each of them would be negative. Okay, that's okay. You take a negative sign out of them, every term becomes positive, right? Yeah, you take a look at this. Okay, so I'm going to look at the nth pair. Okay, this is going to be 2k plus 1. Okay, this would be right. So when n equals 2k, so that's positive. That's 1 minus 2, 2k plus 2. Okay, let's see how does it look like. Okay, so you will get 2k plus 1 and 2k plus 2. Okay, and then 2k plus 2 minus 2 and 2k plus 1. Okay, so what do you get? Okay, so you get 2 minus 2 canceled out, right? 2k plus 2 minus 4k minus 2. So that is negative 2k. Okay, now after simplifying, you get negative k and 2k plus 1 and here k plus 1. So now I'm believing that this is going to be divergent. Okay, so the reason is it's divergent is you look at the partial sum, right? Partial sum, the last term here is 2k plus 1 minus 2k plus 2. So this is when n equals 2k, when n equals 2k plus 1. So the partial sum when n equals s2k plus 1, okay? Those are the partial sum. So the partial sum you end up with when k equals 0, yeah, when this is a general term, Okay, you add all those, those pairs together. So that is, I can use I, okay? I start from 0 to k, okay? And then every term here, you get I, 2i plus 1, and I plus 1. When I equals k, that will be the last term. Now, clearly, this is a divergent, okay? You can take a negative sign out. Okay. The reason it's divergent is because by the limit comparison test, because I and I, it's almost I plus 1, it's almost equal 1, and then have this. So it's clearly this approaches negative infinity, okay? As k approaches infinity. So this one does not have a limit. Wow, this is a good problem, okay? It can be a bonus problem. Yeah, you have to go back to the original argument. You cannot use any of the tests, okay? Use the original argument for the alternating series test. Then we group together pairs by pairs, and every term here become negative term. Of course, if you take a negative sign out, then every term becomes positive term. So clearly this is still divergent, okay? So that means this series, Cn, n plus 1, x to the n plus 1. Okay. N plus 1 is divergent. What I got here? Yeah. Oh, I even forgot to the negatives plus 1 here. Okay. Yeah. Well, if I put a positive sign here, then that was a negative sign plus here, then be much better. Yeah. Okay, so just slightly different. I just changed the sign here. Put here. So every pair of this, you already get positive. Okay, so this is a positive terms. So yeah, this is a positive term. Okay, so this actually is divergent. Okay, when it's divergent when x equals negative. Okay. So that is a good question, So the interval convergence still the same. Okay, interval convergence still the same. So today we're going to, let's take a look at some other interesting examples. I think my favorite example is this one. Okay. We already know that 1 over 1 minus x is going to be, okay, and this holds when x is less than 1. Okay, this is identical. On the left-hand side, it's an elementary function. Okay. All right, so I'm going to apply the above theorem to see what I can get. Okay, this is identical. Okay. Now the function on the left-hand side is defined for x not equal to 1. But it's not going to be equal to the series on the right-hand side, because the series on the right-hand side is only convergent when absolute x is less than 1. Right. So I can differentiate. And I know that this still should be the same for x greater than 1. This holds, right? So the series on the right-hand side still have the same radius convergence. So this is going to be 1 over 1 minus x squared, and here you cannot change, index n start from 0. You can change it to n start from 1. Okay, here's n plus 1. Okay, how can I see that? Yeah. No, you can express in this form. Can you see that? Yeah. So you can you see, change the index. So first one, n start from 1. Okay. Then you let n to be n minus 1. So then m start from 0. N is going to be m plus 1 and x to the m. Okay. All right. So you get this. And you can continue differentiate. Okay. Then you get other formulas. So how about the integral? Okay, let's start from 0 to x. I'm going to use a definite integral. Okay, so this side is n plus 1 x to the n plus 1. Okay, and this also holds when x is less than 1, right? So how can I evaluate integral on the left hand side? The integral on the left hand side is going to be natural log of 1 minus x, actually. And then the absolute negative. Okay. So this is going to be wow. So you can put the negative sign to the left hand side, not to the right hand side, yeah. All right. It's interesting, right? Now from here you can also see, yeah. So let's write down the details. Okay, this is a negative. When n equals 0, I have just x, right? Then plus 2x squared plus 1/3 x cubed, and so on. Okay. So that is a formula for natural log of x. Okay, and this holds for x less than 1, because when x equals 1, natural log of 0 is undefined, right? Yeah. How does it look like here? So x, this is y-axis, this is x-axis. Here's what? X is between, so this is an interval, negative. So the graph of natural log of 1 over 1 minus x is actually when x equals 0 to 0, okay? So this is a graph. Okay? This is a graph, y equals natural log of 1 minus x. Okay? Right, this is a graph. So for this function over that interval from negative to positive 1, I can express as a power series. But this power series itself will be divergent over this on the left-hand side of negative 1. So they only matches over that interval. Clear? Now, if I can change, if I want to change the sign, we can change negative x to the positive x, right? So negative x to the positive x, you just replace x by negative x, right? Okay, this will be negative x to the n plus 1. So you take a negative sign out, be negative 1 to the n plus 1. Okay, then you multiply this negative 1. Yeah, move negative 1 to the inside. So it will be negative 1 to the nth power. Okay, so this is another interesting formula. Okay, this also holds for absolute negative x less than 1, so that's the same in quad. Okay. All right, and so we have a few examples here right now, right? We have the, yeah. So now what we can do is we're going to modify this series to get the power series for the other function in the same form. Okay, for example, okay. Yeah, let me give the definition first. Okay, given a function, so if f of x is given by this formula, okay, and then for such that it's convergent to, yeah, it's a, you know, it's a rate, yeah, over the, if the function is equal to some power series, okay, and that power series of course has a radius convergence. So if this is a hold, this is a radius convergence. Okay, then this power series is called, and the power series will be unique, so it's called the power series representation of f at the point A. Okay. And actually it's unique. Okay, that's a unique. You can prove the uniqueness if it exists. So given function, you can always find, and not always, you know, sometimes you can find, sometimes you can. Okay. So if the function is equal to this power series over the interval of convergence, then we say this power series is called the power series representation of the function. Okay, then I can ask the question. Okay, following question. Find the power series representation for in the form. I have to mention what is it for. Okay, for the function f of x. All right, so that means for the power series, more precise power series representation at, no, more precisely, right, at a equals 0. Okay. So I have to find the power series. It is convergent nearby 0, and that should be also equal to 1 over 1 plus x. Okay, so how can I do that? I use the following fact. Okay, I know that this is pretty close to this function. I know this identity. Okay, this holds when x is less than 1. So I can let x to be here to be negative s to be u squared, for example. Right. Right. In the above identity. Okay, so absolute of x, no, sorry. Okay, let's do the other one around. Okay, this is a fact we know, right? So now, in this function, I can express in this way. Okay, so it's to compare this, right? So it's the same, similar form. So in the place of x, I replaced by negative x. So this holds above by the above identity. It's held to be negative x squared to the power n as long as negative x squared is less than 1, right? So that is going to be, okay, and this inequality is the same as this inequality. So we have this following identity. Great. Okay, we have this identity. Great. Then there's a byproduct. Why? Well, I can integrate, right? I can integrate on both sides. Okay. So it's 1 plus t squared dt from 0 to x. And that is going to be a negative 1 to the n. And here's integrate each term. I get 2n plus 1, x to the 2n plus 1. And that should be holds for x less than 1. And on the right-hand side, this is just antiderivative, not just arctangent x, or this is another way to describe. Okay. Yeah. So that is. So we get a formula for the arctangent See, we jump to the arctangent x. Okay. Right. Here's the next question. Find the power series representation at, I have to say that, usually it's, this part is not mentioned. If not mentioned means at a equals 0, okay? For the function f of x, x over 2 x squared. Okay, how can I do this problem? Well, the numerator is just x, so don't worry about this x, right? So this is going to be just x multiplied by, so all I have to do is just put x here. I'm going to express it in the form, right? Then I apply the above formula. This part is my x, so it's negative 2x squared to the nth power. That should be holds when this is less than 1. Okay. Now this is equivalent to saying, this is equivalent to saying, right? Okay. So now let's simplify a little bit. Okay. Then you move x into, you multiply every term by x. Okay. And this holds for x less than 1 over square root 2. And this is actually the radius of convergence of this series. So this series is convergent for absolute x less than 1 over square root 2, and it's convergent to this function. So we have this identity over the interval. Find the power series representation at a equals 0 for this function. Okay. So that means I'm trying to find something like that, right? And then for some r, right? I want to show this is true. Now, what do we know? We recall this identity. I think we already got this. Okay, and this is true, right? Yeah, we did this, right? So how do we use this to get the power series for the other one? Okay, natural log. Well, you have to modify the function. This one here is 3 there. 3 minus x, I can take the 3 out. Okay. Then I get a negative 3 natural log, a natural log of 3 and natural log of this. So this is just constant. Don't worry about natural log of 3 is constant. How about this? So this is my x, right, in the above formula. So it's natural log of 3 minus n plus 1. And what is my x right now? X over 3. And this holds when this absolute value is less than 1. Okay. Basically, we already know that this is the answer. Okay. Let's rewrite this again. Yeah, take the coefficients out. Okay, and here's x to the n plus 1, and this is absolute value, x is less than 3. So the radius convergence is 3. Okay, this series on the right-hand side is convergent when absolute x is less than 3. Okay. All right, so that is the answer, right? Now here's the last problem I want to discuss, just a couple minutes. Okay, find the power representation at a equals 3 for the function. Okay, that's just natural of x. See, the function natural of x is defined, right? And here's 1, 2, 3. I want to find the power representation at 3. So I think I'm going to do that for this whole piece. So this radius of convergence, I know that should be equal to 3. How can I do this? So I want to make sure this is going to be Cn here and x minus 3 to the nth power. Okay, so the series on the right hand side is convergent over the interval from 0 to 6. Okay, from 0 to 6. And convergent to the natural of x. Well, so I'm going to get x minus 3. So natural log of x is natural log of, right, 3, similar, plus x minus 3. Clear? So that is going to be natural log of 3, 1 plus x minus 3 over 3. Okay? Then I have a natural log of 3 plus natural log of 1 plus 3 over x minus 3. Now, this is my u, okay? Maybe I can put a negative, okay? So if you still use the same formula, if you're not going to use natural log of, yeah, if you're not going to use the formula natural log x plus u, then you have to put a negative. But if you use the natural log x plus u, and then this is going to be something like that, right? Negative 1 to the nth power, and the u to the nth power, and divided by n plus 3. Right? Yeah, we did that, right? Okay. So, so that is true when u is less than 1, absolute value of u less than 1. Right? Okay. So finally, we get n plus 1. Here, what is u? U is going to be x plus minus 3, right? I think this is n plus, yeah, a plus 1. And here's x minus 3 to the n plus 3. And this inequality is the same as this inequality. Okay, so we get a power series representation for natural log of x. I'm going to stop here, okay?